Welcome to lecture 6.1. We are now looking at angles and radian measure. Okay, so if we have an angle called AOB, let me go ahead and indicate where that angle is. So angle A, and then we go to O, and then to B, consists of a vertex, which is that main point right there, O, an initial side, right here, and a terminal side. How I remember that? Well, initial, think of initiate or to begin. And then terminal, think of terminating or ending, right? To terminate something is to end it. To initiate something means to begin it. Alright, so if the angle is formed by moving counterclockwise, the way we usually move on the unit circle, then the angle is positive, which is what we've done before, right? When we're finding the terminal points. And if the angle is formed, that should be formed by moving clockwise, then the angle is negative. So if we move this way, it is negative. And in this case, on the other version, when we're moving clockwise, initial side is starting up here, terminal side, oops, wrong coloring, initial, green, terminal side, right there. So if we're given a circle of radius 1, which we would call the unit circle, right? The measure in radians of an angle is the length of the arc that corresponds or subtends the angle. So what does that mean? Well, the measure of the radian is the same as the length of the arc. Okay. So some other things to note real quick. If you don't have a unit specified, use radians. So if no unit given, use radians. And remember, radians are the values with pi. Degrees are the ones with something like 180 degrees and so on like that. Okay. So now let's take a look at degrees and radians. Once again, so degrees and Degrees and radians are related. They're basically just two different ways of looking at something. For example, just like how you would say 1 foot is equal to 12 inches, right? They both are the same measurement, it's just sort of slightly different ways of looking at the same ruler, right? The ruler is the same length regardless of whether you say it's 1 foot or 12 inches. The length of the ruler has not changed. So, when we're using the unit circle, there are two different ways to look at the measurement. But first off, we know that 180 degrees is the same as pi radians. Just think in general, if you're telling somebody to turn 180, right? That means they turn entirely around facing the opposite direction. So 180 degree turn is turning to face the opposite direction, and the same thing on the unit circle, the exact opposite direction if we start from 0 will end at pi. So 180 degrees and pi radians are the same thing. And then from that we can create these other two rules on the side. So let's see, if I wanted to solve for radians, just 1 radian, how would I solve for that? Well, I would divide by pi, right? So to get radians by itself, you divide by pi, and you get 180 degrees divided by pi. And that is this equation right here. How would we get the other equation? Well, if I wanted to get 1 degree by itself from the 180, remember 180 degrees is the same as 1 times 180 degrees. So if I start with the original equation here, and then getting it by itself, I'll go ahead and divide by 180 degrees. Which means 1 degree is equal to pi radians 180 degrees, which is the equation right here. Okay, so both of these two equations, which we do use a lot to change between radians and degrees, comes from the initial fact that 180 degrees is equal to pi radians. So if you're ever confused on how these equations are set up, just go back to the main initial idea and then just solve for it. Okay, so why do we have these two equations right here? It's because sometimes we need to convert from radians. Maybe we're given radians, but we need to find out the answer in degrees. To do that, to convert to radians, you multiply by pi over 180. Okay, that's this one right here. That's to convert to radians. To convert to degrees, you're going to multiply your item, whatever it is, by 180 over pi. And note, if no units are given, assume it is radians. That is what I mentioned before. The default is just radians. And the default for your calculator, make sure it's in radians. That is one thing to note. Most of the times the default in your calculator is radians. But sometimes you need to change to degrees when you're solving. And if that is the case, that you need to know how to change your TI-84 to degrees. And I'll try to link a video for that in the resources in Laulima. So now, example 1, express 110 degrees in radians. Well, how do we do that? We want to convert to radians, so that's going to be step 1, converting to radians. So we'll multiply by pi over 180. Alright, so we have our original 110 degrees. We'll multiply that by pi divided by 180. And simplifying, we'll end up with 110 pi divided by 180. We can go ahead, simplify those zeros out, and we're left with 11 pi over 18 radians. Let's take a look at example 2. Express pi over 3 radians in degrees. Okay, so we want to go to degrees, so we'll use the second step. So we'll start with the pi over 3, and we'll multiply it by the 180 over pi. The pi's cancel each other out. And then we have 180 divided by 3, which also simplifies into 60. And oops, I forgot my degree symbol there. Do remember your degree symbols. There we go. So the unit is radian here and degrees on this one. Both are important to write down to distinguish what kind of a number you have. Now let's take a look at standard position. Alright, so an angle is in standard position, or an angle in standard position is drawn in the xy plane with its vertex at the origin and its initial side on the positive x-axis. Two angles are coterminal if their sides coincide. So what does that look like? Well, real quick, so we have our unit circle. Well, that's somewhat a circle. And then we have our x-axis, right? So it's drawn in the standard position with its vertex at the origin. Okay, so there's the vertex, V. And then the initial sides, remember the beginning side should be on the positive x-axis. And two angles are coterminal if their sides coincide. So, let's see. Find two angles that are coterminal with the angle theta, this is theta right here, theta equals pi over 6 radians. So how do we do that? What we're going to do is you're just going to add or subtract 2 pi. And that'll end up, if you add or subtract 2 pi, you'll end up at the exact same point, just at a different version of it. Okay, because once again, remember on the unit circle, you could just keep going around and around and around and slowly building up on bigger numbers. Think of a wheel, right? Rotates a bajillion times. So, to find new numbers, we'll just either add 2 pi or subtract 2 pi from the value we're given. And we are given theta equals pi over 6. And we want to find a new coterminal angle. So one option, we could go ahead and add 2 pi. When we add 2 pi, let's go ahead and create the same denominator, so that'll be 12 pi. So theta is going to equal 13 pi over 6. That is a new coterminal angle, and that is in radians. Another one, we could go the opposite direction. We could subtract 2 pi. So if theta originally is pi over 6, we're looking for another coterminal angle, so this time, let's subtract 2 pi. Okay, creating the same denominator again. So multiplying by 6, so 2 times 6 will be 12. Then we have pi over 6 minus 12 pi, so that'll be negative 11 pi over 6 radians. Okay, and you could just keep adding any multiples. You could add 4 pi, 6 pi, 8 pi, something like that, or you subtract away. Basically, that is how you would find possible coterminal angles, and here are 2 of them. There are many, many different possible coterminal angles. So now let's find 2 angles that are coterminal with the angle theta equals 135 degrees. Well, the same thing. We'll be adding versions of 2 pi, but if you recall, or if you notice, they give us in terms of degrees. So we're going to work with degrees. Now usually, if you remember, pi is equal to 180. But to find coterminal angles, we need 2 pi, right? So to find 2 pi, we'll multiply this by 2 to get 2 pi. And 2 pi is 360, which, hopefully you know, right? I think it's skateboarders do it a lot or something. A 360 turn, right? That's to return exactly where you came from. You go from the starting point and you go whoop, right back to where you came from. So we're going to go ahead and add or subtract versions of 360 from 135. Alright, so starting with our theta angle of 135 degrees, let's go ahead and add 360 degrees to it. Adding 360 degrees, we get 495 degrees. Now, instead of subtracting, why not add another version of pi? Let's add 2 pi to it. What would 2 pi be? Not 2 pi, sorry. Let's add 4 pi to it. So multiplying by 2 again, we'll get 4 pi, which is going to equal 720. So another coterminal angle of 135 degrees, if we add to it 4 pi, which is 720 degrees, we'll end up with 855 degrees. And once again, please include that little degree symbol, as that is the unit. Now example 5. Find an angle with a measure between 0 degrees and 360 degrees that is coterminal with the angle theta equals 880. Ooh, okay, so now we have restrictions. We can't be going quite so gun-ho crazy as we were. We need it to be between 0 and 360, and currently it's pretty far off. But let's just whittle away slowly, take away 360 degrees, or remember, 2 pi. 360 is equal to 2 pi. Let's slowly whittle those away until we get close to 360, or in between 0 and 360. So we'll start with theta equals 880 degrees, and we'll minus 360 from that. And what do we get? Well, we have 520 degrees. 520, that's still not between 0 and 360. So we need to take away another 2 pi. So let's go ahead, subtract away another 2 pi. So subtracting away 360. We'll end up with 160. Now, is that in between 0 and 360 degrees? The answer is yes. So there we go. We have found an angle that is coterminal with 880 and in between 0 and 360 degrees. So note, 520 was also coterminal with 880. The other thing is it did not fit our restriction, which is why we had to keep going until we found one that did fit our restriction. Now let's take a look at arc length. So, in a circle of radius r, okay, so we're talking about from center to the outside, so radius r, the length s of an arc that subtends a central angle of theta is given by two formulas. So s equals theta times r, or another way to look at it, if you divided both sides by r. So once again, if we started with the original one right here, divided both sides by r, we would end up with theta equals s over r. So two different versions. Does it matter which one we use? Well, sometimes it's easier to use one over the other, so it does depend on the situation. But they are the same kind of equation. They come from the same thing. So let's look at example 6. Find the length of an arc of a circle with radius 3 feet that subtends a central angle of pi over 6. One thing to note before we continue on. When we're given theta, theta is in, drumroll, radians. Okay? Theta is in radians, which means we're talking about the pi values here, right? Not degrees. So in example 6, it says find the length of an arc of a circle. Okay, so we have a circle, has a radius of 3 feet, and it subtends a central angle of pi over 6. And what do we want to find? We want to find that length right here. Well, let's use a formula. So s, which is what we're trying to find, is going to be equal to r times theta. And our radius is 3. And our angle is pi over 6. And it's already in radians, so we don't need to convert it. Awesome. So multiplying those together, the 3 and the 6 will cancel, and we'll be left with pi over 2. And we need to remember our units. This was in feet. Pi over 2 feet. Next, find the length of an arc of a circle. Oh, let me leave this down here. With a radius of 8 inches that subtends a central angle of 60 degrees. Okay, so we're given this. Wait, I'm going to do another circle. Okay. That is... no. One more circle. Oh, my pen was so horrified it stopped working on me. There we go. Okay, so that's a little bit better. Now we have the length of an arc, a radius of 8 inches. Subtends a central angle of 60 degrees. So something like this, 60 degrees. And we want to find S, the length. Well, we know the formula. S equals R times theta. We'll go ahead and plug in our R value, which is 8, and our theta, which is... wait. Theta is supposed to be in radians. We are given degrees. We need to change this. So how do we figure out how to change 60 degrees to radians? Well, we can go ahead and use the formula. So that'll be 60 times, and we're going to multiply this by pi divided by 180. So this is changing to get radians. Okay, the zeros cancel each other out. And then 18 and 6, those simplify, and we're left with 3. So our answer is pi over 3, unless you remembered that 60 degrees is pi over 3, which some of you may have memorized. That'll be pi over 3. And that comes out to, and we can't really simplify that, 8 pi over 3, and our unit is inches. So that is the length of the arc. Now example 8. Given a circle of radius 4 inches, let's go ahead and draw this in, radius 4 inches, and an arc length, ooh, this time we're given arc, they're getting sneaky on us. So we're given an arc length of 6 inches, find the inner angle, theta, ooh, in both radians and degrees. Okay, so we're going to use the same formula we always use, S equals R theta, except this time we're given different values. So we're given R, which is 4 inches, and we're given the length, but we're not given theta, so we have to solve for theta. Let's go ahead and plug in the values that we know. So S was 6, and R is 4. So solving for theta, we'll go ahead and divide both sides by 4. So theta is going to equal 3 over 2 inches. These are my radians. Now, how would we figure out what our degrees are? Well, to do that, we'll go ahead and multiply our answer, which is radians. We'll multiply that by 180 over pi. And our answer would be, let's see, we can simplify, that'll be 1 and that'll be 90. That'll be 270 over pi degrees in inches. Okay, so those are two different answers. Now let's take a look at example 9. Find the radius of a circle if an arc length of 9 centimeters subtends the central angle of pi over 7. Okay, what are we given here? I always draw a circle because it's just easier for me to see what we're given. You are not required to draw the little diagram unless otherwise stated. But in these problems, unless you're told to draw a diagram, you don't need to. I just find it helps. Okay, so you're given a length of 9 centimeters and a central angle of pi over 7, and we are told to do what? Find the radius. Ooh, I just realized I labeled this wrong. The 9 centimeters is not the radius. That is the length of the arc. That is 9 centimeters. And we're told to find the radius r. Okay, so we know the formula, S equals r theta. And we're trying to find r this time. And we're given S and theta. And remember, theta is in terms of radians, and at the moment it is currently in radians. Pi over 7 is radians. So we can go ahead and solve. Plugging in s, which is 9 times r, and then our radians, pi over 7. Now to solve, okay, because pi over 7 is a fraction, I'll go ahead and multiply both sides by the reciprocal, 7 over pi. And those guys cancel, and I'm left with 7 times 9. What is 7 times 9? 63 over pi r. Oops, equals r. And that is centimeters. Okay, moving on. Area of a circular sector. In a circle of radius r, the area, okay, so now we're talking about the area, not just a length, the whole area of a sector with a central angle of theta radians is given by this formula. Area equals half r squared theta, which is kind of similar to the area of a triangle, right? Area of a triangle is half base times height. And this is sort of half your base times, you could kind of oddly, roughly call that your height. Not really, but it's a way that I decided to memorize the formula. Alrighty. One other thing to notice, once again, theta needs to be in radians for this formula. And then, another thing to notice, a sector is a part of a circle. So think of it as like a slice of pizza from your circle. That would be a sector. So if you're ever at a party next time, you can just go up to somebody and say, I'd like 2 sectors of that pie. And then let me know what they say to you. Okay, example 10. Find the area of a sector of a circle. Okay, so we want area. With a radius 5 centimeters and a central angle of 120 degrees. So let's see. We've got a circle, radius in red, of 5 centimeters and an angle of 120. So somewhere over here, 120 degrees. And we want to find the area. So this whole thing is what we're searching for. So the formula for that is area equals half the radius squared times theta. So half, and r squared, r is 5, so that'll be 5 squared. And theta, ooh, at the moment theta is in degrees, and we can't use that, it needs to be in radians. So we gotta go convert theta. So 120, now to convert to radians, we'll go ahead and multiply this by pi over 180 degrees. The zeros cancel, and let's see, 12 and 180, they both share 3. So that'll be 4 and 6. Ooh, they both share 2. So that'll be 2 and 3. So the answer would be 2 pi over 3. You could have simplified that quicker, but sometimes I just like to do that by hand for fun. Okay, so that's our theta value, so multiply that in. 2 pi over 3. And now simplifying away, the 2's cancel with each other, and we're left with 25 pi over 3. And our answer is going to be centimeters, and careful here, we're talking about area. So it should be centimeters squared. Okay, remember that squared value. Centimeters squared for area. Length does not have a square, but area does. Okay. Now, I believe it's the last concept for this section, linear and angular speed. Suppose a point moves along a circle. Let me go ahead and draw a picture. So we have a little point here, and he's moving along a circle of radius r, and the ray from the center of the circle, so there we go, we got the ray from the center of the circle to the point, so to wherever that point has been moved to, what do we know about it? Moves at theta radians in time. Okay? So it's moving at theta radians. And we're given time is t. So we have, let me go ahead and erase my diagram here. We have the original function, the original equation of s equals r theta. And this is going to be the distance that the point travels in time. I did just erase that picture, but that'll be the distance that the point traveled in a given time. Then the speed of the object is given by the formula. Angular speed, so this is talking about the change in theta. There's two different ways to look at it. Talking about the change in the angle, so this change right here in the angle, is given of w equals theta divided by t. How I remember that formula, I was like, what? It looks like right? Nah. If that didn't work with you, that's okay. I just thought that was funny when I was in trig. Okay, so change in theta. So w stands for angular speed. Then we have theta, which is, as usual, theta, the degree, or the radian, sorry. And t, which is time. The other way we could look at this is the thing called linear speed. So it's the change in the distance traveled. So this is talking about if you're standing on the circle and running along the edge, that would be linear speed. And that is VST, or VST. Just my way of memorizing it. And then the other formula for it is V equals RW. There is a way to solve for how to get this equation. If you want to know that, go ahead and send me an email and ask about it. I'm not going to include it in this video. Okay, so example 11. A fan blade of length 3 feet rotates at a rate of 7 revolutions every 2 seconds. Find the angular speed. Okay, so angular speed is talking about the inside angle, which means we're going to be looking for theta. Let's go ahead and draw a diagram, though. We have right here, let's see, our little fan, right? Let's go ahead and draw the little plug for the fan. And we have the fan blades. And we know about the fan blades is that they are 3 feet. I have a feeling that this is not a fan that plugs into the wall. This is probably a ceiling fan to have blades of 3 feet. Okay, then what do we know? It rotates at a rate of 7 revolutions every 2 seconds. What does that mean? Well, rotating, so it goes a full rotation. That's just 1 revolution, okay? Full rotation is 1 revolution. Let me write that down. 1 revolution is a full rotation around the circle, which is also equal to 2 pi, if you're thinking of unit circle. But what does it say? It says it goes 7 revolutions. So it goes around 1, 2, 3, 4, 5, 6, 7 in how many seconds? In 2 seconds. Now it wants to find the angular speed, so how quickly the angle is changing. Well, the formula for angular speed is right here. It's what? So w equals theta divided by t. Well, what is theta in our problem? Theta has to do with how far it has gone around, right? And it went around 7 revolutions. So that's going to be 7. Actually, let me write this out on the side. Theta is going to equal 7 times 1 revolution, which is 2 pi. And that would be 14 pi. So theta is 14 pi. And the time that we have is given in 2 seconds. So simplifying that out, we'll end up with 7 pi radians. Remember, we're in radians. Per, and what's our other unit? Seconds. So since this is a word problem, we would answer that, what is this? The angular speed is 7 pi radians per second. So that is one thing to note. If you ever have a word problem on an exam, you will be expected to answer in word form because it's a word problem. So make sure to just give a nice quick end sentence, capital letter in the beginning, and then make sure to include your numbers, so right, 7 pi, and then your units, radians per second, and then lastly a period, because it is a complete sentence. And we are college people, we can write a complete sentence. Alrighty. You might ask why I'm doing that. That's because that is one of the SLOs, or the student learning outcomes, for this course, is that you can also communicate mathematical thoughts with me in written English, so in written form. Okay, just one of the SLOs, so make sure I can tick that off on your grading. Alright, example 12. A bicycle wheel is 26 inches in diameter. Let's go ahead and draw that in. So a bicycle wheel. Oh, that looks horrible. Let me fix that. I may not get this satisfactory enough, but the next circle I do, I will stick with this circle. Oh, that's horrible. Okay, so we have our bicycle wheel right here's our tire. I'm just going to go ahead and fill in that tire. And it's got spokes and whatnot. What do we know about it? It's 26 inches in diameter. Okay, so this whole length across is 26 inches. 26 inches. And then the wheel rotates at a rate of 120 revolutions per minute. So the whole wheel, if I start here and I go around, it does that whole revolution 120 times in 1 minute. Okay, so now we want to find the speed the bicycle is traveling. So that is going to talk about linear speed. So we're looking at linear speed. And we want to answer in, real quick, I'm going to note this, so we're going to convert to hours in miles at the end. So find in miles per hour. Okay, so we want the linear speed, and the formula for linear speed, we'll go ahead and use V equals R times W. Well, R, what is R? Oh, notice, we're given the diameter. We need to find the radius, which is half of the diameter. So half of 26 is going to be 13 inches. So that is our radius, 13. And then we need to find W. What is W? W is the angular speed, so we got to find that on the side. Angular speed. So what is going to equal theta, and theta is the angle we're looking at. And that was 120 revolutions, so it's 120 times 2 pi. Because each time it went around once, it covered a distance of 2 pi. And it went around 120 times. And then we'll go ahead and divide that by time, which is per minute, so 1 minute. And that simplifies out to 240 pi radians per minute. Okay, so there we go. We have that. Let's go ahead and circle that. So that'll be 240 pi. And then inches per minute. Okay, so that simplifies out to, we'll go ahead and put this in a calculator, approximately 9,801.8 inches per minute. Okay, but once again, we wanted to answer in miles per hour. We're talking about speed here, usual speed. So how do we convert this to miles per hour? Well, at the moment, we have 9,801.8 inches in 1 minute. So at the moment, I have inches per minute, and I want to end up with miles per hour. So I'm going to find ways to slowly multiply this by equivalent fractions until I get to miles per hour. So let's see. Let's go ahead and get rid of the minutes. Well, I know that 60 minutes equals 1 hour. Look at that. I've related minutes to hours. So let's go ahead and multiply by 60 minutes in 1 hour. Ooh, well, the minutes cancel out. That's one step closer to my goal. And I'll end up with, let's see, multiplying that by 60, we'll get about 588,106 inches in 1 hour. Okay, I have my hours, but I need to get rid of the inches. So let's think of an equivalence. Well, I know in 12 inches, there's 1 foot. And in 5,280 feet, there's 1 mile. So I really want to get from miles to inches. How do I do that? Hey, so if I multiply 5,280 times 12, I'll get, so multiplying this out, 0.6336. I'll get that many inches. So 63360 inches in 1 mile. And I have created an equivalence with inches and miles. So go ahead and multiply that here. So I get 1 mile times 63360 inches. Awesome. Now the inches will cancel out. And I'll be left with, multiplying that out, that'll be about 9.3 miles per hour. And we would write a sentence. Sorry, I've kind of run out of room here, but the answer would be, the bicycle is traveling at about, and the reason we say about is because we did do some approximating. It's about 9.3 miles per hour. And box our answer. Alright, that is it for 6.1. These are the practice problems. Once again, they should be uploaded by the end of the week. They are not part of your grading for the summer course. Okay, that is it. Please email me if you have any questions.